Hi, Jim. Welcome to the podcast, Everyday Metallurgy.
Yeah, hi Peter. Nice of you to invite me. I think it's going to be a great discussion.
I'm sure. Today we're going to talk about something that when I was introduced to it was very big. But today I think you're also making small, tiny things because we're going to talk about HIP, hot isostatic pressing. It's
Right.
it's one of the younger kids in the metal powder business, as I see it. But it's one of those growing extreme these days because there are new applications coming in. Um,
Might not be as small as you think though, because we're involved in a lot more areas than you might imagine, actually.
I could imagine, yeah. But first, would you give an introduction to yourself and the company you're working at?
Yeah, so my name's James Shipley. I'm English from the beginning, but I've been living in Sweden for many years, and I'm the manager for the business development team here at Quintus, and basically involved in a lot of different customer projects and different university projects. And I'm working a lot with different customers around the world, based in Sweden. And my background is really, I'm a physicist once upon a time in the West, back from the UK years ago. My background is really with Sandvik for many years, working with the material side for 28 years. And I've been at Quintus now for 8 years. And I'm working mainly with hot isostatic presses, but we also do other kind of isostatic pressing equipment as well.
Perfect. Thank you. So if we look at the HIP, I said it's a new boy in glass, but can you give some insight in the history of HIP? When was the first HIP built, and who did that, and why did they do that?
Yeah, it's an interesting story, to be honest, because at the time, densification was a very interesting topic that was being looked at for the nuclear industry by the Battelle Institute in the US in the early 50s, late 40s, early 50s, for densification of fuel elements, etc. And that was kind of an area that was looking at how can we contain very high pressures in order to densify materials. And at the same time, ASEA, the Swedish company, state-owned company once upon a time, which actually is our origin, we come out of ASEA. ASEA was a big conglomerate in Sweden that later became ABB. Or the A in ABB. And ASEA were working on synthetic diamonds at the same time. So they were looking at how could we use incredible force basically to create man-made diamonds. So there were two independent pieces of work going on, really looking at densification and how pressure could be contained. So in the early 50s, ASEA went ahead with the diamond presses, and Battelle were developing the isostatic presses. And the first real HIPs were manufactured and became industrial in the 60s. We still actually have a machine in operation from 1965. Wow. So these things last a long time. And over the years, the isostatic pressing and hot isostatic pressing, especially for us, became very interesting then for different kinds of materials as time went on. And I guess a lot of people may be aware of densification applications that the HIP is used for, and amongst others are powder metallurgy capsules that are densified into solid parts, and that really came in the 70s in a big way. So it's a long history really, but Quintus, we were renamed Quintus in 2016, but we're actually from a spun off from ABB during the 80s. And our origins are with ASEA.
Yeah. So if we look today, what are the main usages? I have seen some of the new ones are these 3D printed material where it's not densified, there's still porosities. Then you can close the porosities by hipping. But what are the main newcomers in the industry?
Yeah, I mean the newcomers. There are newcomers every day in different application areas. Basically, I mean, HIP is a pressure vessel, you could say, with a furnace inside it. So and that's basically what we're doing. We're heating material inside the HIP, and then densifying it at the same time with incredible pressures, which are, I mean, a typical HIP pressure is around about the same as the pressure at the bottom of the Mariana Trench, just to give you an idea. So it's above 1,000 bar or 100 MPa.
Yeah.
And with this and a furnace inside, we're heating the material, softening the material a little bit, and getting it to relax, so that the pressure can then densify and remove voids. So I think densification is the main area that everybody knows about. But there are really, for us, four main areas for hipping today. One is densification, because castings have been densified since the 60s to improve fatigue life, etc. We have powder capsules, densification of powders, which is, like I say, since the 70s, really, which is really growing right now. It's a very interesting area. And then you have diffusion bonding of materials together, and that can be solid to solid or solid to powder or powder to powder. Basically diffusion bonding different materials together. And then the fourth one that we're mostly working with today, I would say, is doing the heat treatment inside the HIP. And this is where the AM discussion comes in, because we can shorten the supply chain basically for AM components by densifying an almost dense part, and improving the fatigue life of that part at the same time doing the heat treatment and setting the microstructure. So that's kind of where we're acting today. But the powder metallurgy area is really growing, and that's an interesting one.
That's good to know, coming out of the powder metallurgy family. I've sometimes visited a HIP facility, and looking at, I think the biggest one I've seen was something like 10, 12 meters tall, and 2.5 meter wide, and you could put in many tons and HIP it. But how do you build it? What are the main components of a HIP machine?
Yeah, I mean, there are different designs out there on the market. Our specific design is based on technology that was developed during the Quintus project, actually at Attasia in the 50s for the diamonds, which is wire winding of forgings. So we actually take forgings that we have sub-suppliers for, that we then wind with a metal wire, or spring steel, you could say, which is putting compressive stresses into the forgings. And the amount of wire winding, the amount of pressure, etc., in order to put compressive stresses into the forgings, it depends on the size of the machine and also the pressure rating, etc. And basically, we're creating a forging that's under immense pressure itself, so that when we put gas inside and we pump the pressure up, the wire is kind of forced out again, but it never past the design point. So we have obviously a design point to keep the wire from relaxing too much. So it's wire winding is what we use, and we do this also on a frame, which is also made from forgings but wire wound together, which is a bit like for a champagne cork. You have the cage to keep the pressure inside. And in our case, we have a frame that goes round on both, keeping both of the end closures in place. So we have circular forgings that are, the lids, if you like, of the cylinder. And then we keep that in place with this frame, which is then taking up all of the tension, because there's enormous forces involved in in these machines.
Yeah.
So it's we're talking meganewtons of pressure on these lids. So it's a lot of pressure to look after, but this is our design. And the good thing about this is that we have the ability to cool in the equipment as well, because we've built that into the design. So this is why we've then developed this technology over time now, looking at how to control the cooling in the machine, actually how to steer this exactly according to customer wishes to do the heat treatment inside the hip. So this is our kind of main area of interest.
I remember I was told that the lead, when you put it on, is not tight, but then when you start to heat up, the cylinder expands and then it becomes tight. Is that the way it is?
Yeah, and of course there's lots of tricks and everything in the designs, but the gaps, the expansion of the materials, and the way of handling the pressure and actually keeping the pressure inside at 1,000 degrees C or 2,000 degrees C is quite a task, and that's where a lot of the design aspects come in. And there are different designs on the market, let's be honest. But I think Quintus is a leader. We've been around for many years on this area.
Yeah. You just touched upon it. These 1,000 degree, and you said 2,000 degree. Is it Celsius?
Yes,
is
Celsius. Yeah, I mean, typical design, I mean, machines can be designed or tailor-made for customers, of course, but most of our standard equipment is designed for 2000 C. And I say the graphite units, the molybdenum units are designed for 1400 usually. When I say molybdenum units, I'm talking about the furnace materials here. And
the heating elements.
And the heating elements and all of that. So the furnace includes the elements and the mantle and other parts. But then the pressure rating is usually 207 MPa, which is 30,000 psi. So with the American units. So this is the typical design for a standard machine. If you buy we have today I think we have 12 standard designs of the equipment, and then different furnace options, etc.
And there's a lot of isolation in the walls to avoid the vessel to become hot, I guess.
I mean, basically you have what you call a mantle, which is like how to describe it. It's like a cylinder with the end cut off, basically, that you're putting over the components. And that cylinder, that mantle has the heaters inside, and also a lot of insulation. So this is keeping this is the actual furnace, if you like, where all the tricks are done with the heating and everything. But outside of the mantle, you have a cold gas area, which is towards the wall of the pressure vessel, and this is in order to keep the temperature uniformity. We can exchange those gases as well, but also we use that for cooling, for that cool gas. But the main reason is actually to keep the wire from overheating in the pressure vessel, and to keep the metals in the right temperature range for their behavior, expansion, etc.
How's the power level in such a machine? Are we talking megawatt or what level are we at?
It depends on the size of the machine. So I mean, the smaller machines use a lot less, of course, than the very big ones. And you can imagine, I mean, the machines that you're talking about I think that the largest one in the world at the moment that's in service is a 2.05 meter diameter hot zone, and 4.2 meters high. And that's a Quintus machine that was delivered to Himeji in Japan, to MTC company. And that one is I don't know the actual power rating for it, but you can imagine the amount of material. I think the largest powder metallurgy part that I think's been done there is 18 tons. So there's quite a lot of heating need for an 18 tons component.
So they're quite big cables going in. through the
Yeah.
wall? So you're making holes in the wall and sealing it?
Not in the wall, but through the end closures. So you have, depending on the design, you have feed throughs in the to get the electricity in there to the heaters. Yeah. So the designs are complicated, but I think that's the nature of the business really. When you're trying to keep one of these, keep the right temperature in the right hot zone or the part of the hot zone, and get electricity in, and also get the heat out when you want to cool.
Yeah, absolutely. What is typical timeline in one run?
It depends on the material. And it depends if you're including the heat treatment in the step as well, because in our equipment you can also do the aging steps inside the hip. So you can do, as an example, a preheating or stress relief. You can do the hip cycle itself, densification. You can do solutionizing, and also then aging. If you have capacity in your machine, you can do that, and if you have your own equipment. But if you're just looking at the hipping part itself, it depends very much on the dimensions of the part, the thickness of them. Obviously, powder capsules can take a while longer than a thin AM part. But in general, maybe for titanium, we're talking cycle times for our equipment of around about 7 hours. For a nickel alloy, it can be longer depending on the standard. And it's also a little bit connected to the amount of pressure that you need and the temperature involved. So the higher the temperature and the higher the pressure, of course you have to do more pumping, more heating, etc. But then usually in the specifications, they talk about the whole time for the hip cycle. So if it's maybe 2 hours at 900 degrees C, 1000 bar, this is a kind of typical titanium cycle. Those kind of standards are out there. And then they don't often talk about the heating rate and the cooling rate, which is an area where we're quite advanced, I would say, in terms of heat treatment cycles.
Yeah. And the gas, is that always argon, or has that been made tried with other gas?
It's predominantly argon, but there are some materials that are hipped in nitrogen, and such as silicon nitride, as an example, ball bearings for electrical vehicles. These are hipped in nitrogen. And then because nitrogen and molybdenum like each other a little bit too much, usually graphite units used for those graphite furnace in order to use the nitrogen atmosphere.
Yeah, good idea too.
But it's mostly argon. Most of the components out there in the world are hipped in argon.
Yeah. You talked about nickel-based or titanium-based, but can you do anything? I have seen a lot of tool steel. That's the world I came from. But what about non-metallics? Can you also hip ceramics?
Yeah, ceramics are very common. Ceramics are very common. As an example, zirconia toughened alumina, which is used for medical implants for I don't know if you've seen these kind of pink ceramics that are quite often seen on pictures for hip stems, the ball, these kind of things. Those of course are a good example of what ceramics are done. Also, transparent ceramics are usually hipped to remove the pores that can be refraction points for the light. So those are kind of good examples, but there are many ceramics are hipped, and also we've done other materials as well, not just metals and ceramics. I mean, even plastics could be hipped, just at lower temperatures. So lots of things have been tested over the years.
Plastics, I didn't know that.
We don't. It's not a common application. It's just one of those things that you can test now and again.
But all the materials you put in, they are, you could say, inert in the process, or do you also have activity, metallurgical, going on during the process?
Yeah, well, usually you don't want to have any activity, usually. So that's why argon's used. But of course, when you open the container, if you like, and you're putting in components in the hip, they've of course been exposed to the atmosphere. You may have some contaminants on the components and things like this. So usually there's some pumping cycles or vacuum cycles to remove reactive elements from the cycle prior to hipping. And this is just an industry standard. But even if you've done that, you usually don't get rid of all of them. So there can be some small reactions in the hip, and you see sometimes some discoloration of components that have come out from the hipping cycle. They can look a bit oxidized. And this is due to the partial pressure of oxygen, which is extremely high when you get to 1,000 bar or 1,500 bar. The partial pressure of the oxygen goes up, of course, and that's a reaction with the metals is quite common. So we've actually developed a way of handling that these days called Quintus Purus, where we can avoid the oxidation of the components. So that's kind of something we launched last year. But it's just because there are some reactions that maybe you don't want to have. Usually you're not doing active reactions in the hip. That's not something that is normally desired. So
I could imagine that if you want, you could take when you make a capsule with powder inside, you could make a single. If you want chromium carbide, you could mix chromium and carbon powder and have a reaction in situ, but that is not something you do.
I mean, when it comes to the capsules, we manufacture the hip equipment, and of course our customers are the ones who are making the capsules and filling them with different powders. But there are metal matrix composites. There are composite materials that are made in capsules today, where powders are mixed, different materials are mixed. Could include ceramics in some cases. It could include some solid wrought parts as well. So there are different ways of doing it. But for the capsules themselves, you can put some actually functionality in specific areas where you want it, like a wear resistance or a corrosion resistance in a given area, by using a different powder in that area of the capsule. And then when you densify it, of course, you have a multi-material capsule with some functionality where you want it. And this is also coming now for additive, where multi-materials are being printed now. There's a lot of discussions around directed energy deposition, example with powder, where you can spray different materials basically into different areas when you use in the laser, and then get multi-material parts from AM. And of course, densification, changes in or the risk of dissimilar materials means you can maybe get some pores or some cracks or whatever that want to be healed. So HIP is used. For the powder capsules, it's always used. But it's an interesting area with multi-materials, and I think composites of different kinds are being developed. High entropy alloys is a typical one, I think, where you see the maybe 5 elements that don't want to be together, and you can put powders in a capsule and hip them together, and you get a great high entropy alloy. So those kind of things are going on.
So in situ material building is absolutely possible.
Basically,
When you do that kind of experiments, you might sometimes make a mistake. Oh, the leakage was a bit lower than I expected. So have you ever seen fatal errors where it melted in the hip instead of just
there are, of course, been cases over the years. I think it's not very common because most customers have very good control over what they're doing. But I think a typical example is when you if you use a software like Thermocalc, you can look at the interaction between materials, and quite often if you have 2 dissimilar materials together, actually the liquidus point can be different than for the two materials individually, and those things you have to keep an eye on so that you don't get material melting into the furnace base of the hip. And of course, things happen occasionally, but it's usually when people haven't thought properly or asked for help. And we have an application center here in Sweden and also one in the US where we're doing lots of trials for customers. So we help them a lot of time with these discussions, what temperatures to use, what pressures, etc., what cooling rates, heating rates, to avoid issues with the material.
That's a good idea, because I could imagine if you were out of control of your liquidus, it could be a big mess in such a machine.
It could be a big mess, and not just a big mess, but an expensive one. And I think to clean a machine, if something like that happened, would be quite expensive. So
this channel, it's called Everyday Metallurgy, and everyday is because I would like to relate it so people can relate to what they see on their everyday basis. Are there any products being hipped that I can find in my kitchen or in my car or in my everyday life?
I would say people's everyday life is touched by hip every day. And it's one of those things that maybe you don't think about how the material's been made or processed. But in reality, I mean, if you fly on an airplane, the engine materials, the turbine materials have gone through a hip. And this is just to improve the fatigue life of the blades in the turbines. This is a typical example. Could be other parts on the aircraft as well. If you look at, I mentioned earlier, medical implants, hip joints. If you get a new hip joint or a new knee, they've gone through a hip, or a new ankle joint, etc. Those kind of typical applications. And I mentioned also the silicon nitride bearings as an example. A lot of the electrical vehicles today, if you buy an EV, they have a very high rotation speeds on the drives, on the axles, and 20,000 RPM or above, and a normal steel bearing has problems with that. So a lot of the vehicles have already gone to silicon nitride bearings, and those are hipped again for fatigue resistance. So it's a typical example. I mean, there are hundreds and thousands of these, and of course we're pretty much everywhere where you have a material challenge that you want to make sure the parts last as long as possible. They go through our hips, and I think the energy industry is another example. Turbine blades for industrial gas turbines, typical one. Parts for nuclear power plants. All this discussion around small modular reactors now, which are starting to come as a real item to produce power. A lot of those parts are hipped just for safety.
They are nickel-based super alloys.
Not always.
Are they single crystals?
So it could be some. I mean, different applications, different things. Some turbine blades could be single crystals, can be nickel alloys. If you're looking at the energy industry for like SMRs, there can be different materials in there. Some nickel alloys, some stainless steels, some carbon steels, all kinds of different materials in one of these nuclear power plants. And for safety, and to prolong the life of the equipment, these are hipped. And then of course the spare parts for these kind of nuclear power plants that have been running for 50 years. You can't get hold of the spare parts so easily. So quite often these are manufactured using powder metallurgy, near-net shape, to make a component very quickly with extremely high quality. So those are there's some typical examples, maybe not touched by you every day, but if you're using electricity from a nuclear power plant, then you're definitely using hipped material. Just some examples, but I mean, I guess there are a lot more.
So if we look ahead into the future, has HIP peaked? do you still see a great future for HIP?
It's expanding rapidly. The cake, if you like, is getting bigger every year.
Yeah.
And I think that's because the AM is one driver, of course. But as the powder producers want to take their cut for the AM laser powder bed fusion, as an example, cuts of the powder, there are still some larger cuts that they don't want to waste, and those are people are looking for new applications, and of course there's powder metallurgy there for powder in inert shape.
Yeah.
And at the same time, there's been some major projects being driven, as an example, in the US for a super large HIP called the Atlas project. And this is driving then powder metallurgy to replace forgings in the US. And I mean, one of those components could be 70-ton load in that HIP in the future.
70.
70, yeah. So 70 tons of powder in a capsule. You can imagine it's a lot of powder that's needed. So these applications are being driven by end users, and at the same time, the powder producers want to find a use for the powders that they've produced.
Yeah.
So that's a kind of a perfect storm. And also AM is, as you know, growing rapidly. I think the latest unparalleled report says 17% growth in material use or something like that. And 17% per year growth is quite a lot for material use. And basically, the space industry today, all of the rocket engines are printed. So it's that's a good thing to think about. The number of rockets you see going up on YouTube every day or whatever. It's a lot, and that volume is growing.
You don't look at the satellites. You look at the rockets.
Well, the rockets, but also the satellite frames. The satellite frames are hipped. A lot of those are manufactured by AM as well in titanium. So there's a lot of applications out there that maybe you don't 100% think about from the beginning, but there's a big a growth in the use of HIP, and the traditional volume, I guess, is still from powder metallurgy capsules like high-speed steels, powder in inert shape, and castings. Those are the three big users of HIP today. But then there are other areas that are growing rapidly.
Yeah, this mega piece of 70 ton, is that tool steel? And I could imagine it's when you cast such a big piece, you have a lot of segregation going on and big grains in the core due to a low cooling time or a very long cooling time. Is it to avoid that you go for such a big HIP?
I mean, the big discussion in the US around powder metallurgy has been around replacing forgings, actually. As they want high quality material that can replace forgings that may be difficult to buy locally. That's the big driver. But then castings, of course, large castings also benefit from densification. So, of course, they could be potentially in a HIP machine. The HIP's a bit agnostic. It doesn't really care what you put in it. You will just densify based on the parameters you add, the temperature, pressure, cooling rates, etc. So that's a big machine can be used for many things, and today the service providers out there in the world, they're hipping pretty much everything. Different runs, different days for different materials, and servicing any customers that really that want to improve the properties in the materials.
And this thing you talked about by introducing that you can now in situ make the heat treatment as well. That's also a little unique, isn't it? Is that also growing, or is it just something nice to have?
I mean, we obviously can't talk about customers and who's doing what, but some of these newer materials that are being used have specific cycles developed together with us where we're doing the heat treatment directly in the hip. One of the big benefits is that if you do heat treatment outside the hip, you densify the pores, and then you can get some thermally induced porosity again when you reheat the material, because the temperature for the hipping is usually very close to the solutionizing temperature for the material. So you can imagine that you could get potentially some pores reopening, and that's the quality is seen as better when it's been done inside the hip. Another benefit is that you use less energy. You don't have to reheat the material. So this is a sustainability aspect as well.
Yeah.
And there are customers today doing hipping directly on the build plate, as an example, for AM. That, if you have parts that come out of a printer, they depowder and clean the build plate. They put the whole build plate in the hip, with the parts still on, and then they do the hip cycle, doing the stress relief at the same time on the way up. So you avoid doing the stress relief first, the hipping, and then the solutionizing. And then, of course, you can decide whether you want to do the aging, which can be very long sometimes, in another machine, or do it in the hip. But that can be done also. So it's and this is kind of where some of the customers in the industry are going now with us, where they want to do as much as possible inside the hip.
Yeah.
So one of our latest high pressure heat treatment machines is actually designed for a 600 build plate. So we can do the very large parts inside a large hip, the QAH 200, which is specifically designed to be able to do heat treatment for AM on the large builds. So that's a new addition to the family, actually. So that's quite a nice machine for this also.
Yeah. Jim, I learned a lot now, and I was thinking, if people want to learn more than just watching this episode, where would you advise them to go?
Yeah, and of course on our website you have a lot of information. We have a knowledge center on the website where you can download white papers and information. You can also contact us through the website, or you just get in touch with me or any of your Quintus contacts, of course, to talk to us more. But I think the website is the main area, but there's also a lot on YouTube. We have a lot of videos out there to learn more, and conferences, of course. We're usually at a lot of conferences, so look us up, come and listen to some technical papers. And if you want to work with us, I say that to the viewers, if you want to work with Quintus and develop some hip cycles for specific materials, then just reach out, because that's what we do every day.
Perfect. Yeah, we met at a conference, or at many conferences. That's absolutely recommendation from my side to go visit you and learn more.
Fantastic.
So, yeah. Jim, thank you very much. I'm out of questions.
Oh, perfect. So I hope you got answers to them all, and